This is problem 38. An unknown particle decays into a pair of charged pions. One pion is detected with energy 550 megaelectron volts in the direction of the initial particle's velocity. And it doesn't matter which pion that is, so let's just say this one is 550 megaelectron volts. The other one is detected with an energy of 147, but in the opposite direction, which means the momentum is going to be negative. Also, because one particle is going in the same direction and the other one's going in the opposite direction, that means this is a one-dimensional problem, so we can say the y component for the momentum for each of these is 0. We want to figure out determine the unknown particle, which we can do by finding the rest energy for the unknown particle, because if we look at pages 3 and 4 in the appendix, you are given the rest energy for different particles, and provided that the rest energies aren't really close to each other, you should be able to determine the identity of the unknown particle. So if it was something like a proton and a neutron, you might not be able to figure out whether it's a proton or a neutron because let's say you get 939, that's somewhere in between the two. But for all of the problems that they ask you in the book, it shouldn't be an issue. So, let's look first at the charged pions, and the charged pions have a rest energy of 140. Okay, and then we need to conserve both energy and momentum. Oh, well, look at this. If we know the total energy of the pion, of each pion after the collision, then let's just skip ahead here to the conservation laws. And for energy, we have the total energy of the unknown particle must be equal to 550 plus 147. 550 plus 147 is 697. So let's go ahead and put that in. So we know E total, but the problem is to find the identity, we need not the total energy, but the rest energy. So I'm going to have to do conservation laws for momentum also. Well, if I know the rest energy and I know the total energy, I can figure out the momentum using this equation here, which if we rewrite it, we have PC is equal to the square root of, let's just call it E for E total, so E squared minus the rest energy, which we'll call E naught squared. So for the positively charged pion, which we said is the one that has a total energy of 550, but it doesn't matter which one you say is which, as long as the one with a total energy of 550 is going in the positive direction. So this will be 550 squared minus the rest energy, which is 140 squared. So that gives us 532. So that is the momentum for that particle. And for the other one, that would be total energy of 147 minus the rest energy, which is still 140. And that gives us, it gives us 45, but I know it's supposed to be negative. So can I just say this is the absolute value, and I'll put in the negative sign up here because I know it's going in the opposite direction. So then for momentum, I have the momentum for the unknown particle is equal to 532 minus 45, which is 487, and So then I need to find the rest energy for the unknown particle, which I can again use this equation for, but now rearranging it, I get E naught is equal to E squared minus PC squared to the 1/2. So for the unknown particle, I would get 697 squared minus 487 squared to the 1/2, and that gives me 498.6 mega electron volts. Then I take a look at the rest energies that I have here. So there's nothing like that on page 3. So look at page 4. 498 would be a neutral kaon. So the unknown particle is a neutral kaon. Also, suppose that we rounded and we weren't sure whether or not it was supposed to be a neutral kaon or a charged kaon. So let's say we were somewhere in between 494 and 498. Well, you could also look at the signs that you have for the charge. So if you end up with a positively charged pion and a negatively charged pion, the total charge that you have after the decay is 0, and the charge should be conserved. So if you end up with a total charge of 0, then you should start with a total charge of 0, which would mean it should be a neutral kaon and not a charged kaon. And that concludes problem 38.